Good morning, everyone. Welcome back. Where we're at today is we are just going to wrap up the last couple of properties and examples, well, example singular, for section 15.2, which is multiple integrals or double integrals in this case over general regions. And then we'll get into the next section, which is change of coordinates, where we're going to look at regions that are best described in another coordinate system, namely the polar coordinate system, and look at how we have to modify our integral to work in that case as well. So let's have a look at these properties. Now, these properties of double integrals are all familiar properties from single integrals, and they just carry over for double integrals as well. So that is the integral of a sum is the sum of the integrals. That's the first part, part A. Part B says if you want to scalar multiply a function and then integrate it, you can just integrate the function and then scalar multiply the result. So that's the C can come out, all scalars can come out of the integrals and be left out front as a multiple or a scalar. If f and g are greater than if f is greater than g, then the integral of f must be bigger than the integral of g. Sorry, I was just checking the chats to see if there was a question about this content. The next part is if we have our domain D broken up into two domains that do not overlap, then we can do the integrals over each of those domains separately. So perhaps we're interested in finding the double integral of a function over two circles that are apart from each other. Then we just do the individual integrals over each of those two circles and then add the results. Part E is a nice one in that it relates back to calculus 2. It says that we can find the area of a region by just integrating. Essentially, what you can think of here is we're integrating the constant function 1. If you imagine just a 1 sitting there. So I haven't put the 1 in there because we don't need to write it, but the idea is we can work out the area of a region by integrating over the region of the constant function 1, and that gives us the area. So that tells us that all our results back from calculus 2 about areas of regions can be computed here as well in this more general context of the double integral. So in property, I'm just reading the comments. If they did overlap, would you just subtract off the integral of their intersection? Absolutely, you could do that. Yep, that's a good comment, Graham. That if you did have overlap, then what you would have actually done in each of the integrals, the 1 over d1 and the 1 over d2, it would have counted that integral twice, the integral over their intersection. So you could subtract off the overcounting part of it. The last part F is just a way to get an estimate for integrals. So if F is trapped between two values for all points in the domain, so it's at least little m and at most big M, then the integral of F over that domain is going to be trapped by little m times the area of the region you're integrating over, and it's going to be trapped above by big M times the area of the region you're integrating over. So all of these follow from similar properties for calculus 2, so single integrals. So let's have a look at this next example, and I'll leave the last part of the properties up above there, because what we're going to do is we're going to estimate the value of this integral, where D is a disk centered at the origin with radius a half. Why are we going to estimate? So maybe I'll write this in here. Why estimate? Why not just evaluate? Well, the point is if we're going to want to evaluate or find the exact value, then what we need to do is we need to, looking at this function here, and the fact that the first variable of integration is x, or we could switch it and do y, it doesn't matter. But the point is that e to the x squared plus y squared does not have an elementary antiderivative. Elementary antiderivative. With WRT, so with respect to x, or even y, so either one. So we can't actually just do the evaluation in this case by saying, oh, let's take the antiderivative with respect to x and then evaluate the endpoints and so on, because we're just stuck at the start. Can't find the antiderivative of it. That doesn't mean we can't evaluate it exactly, and I'll make a comment out after we do our estimation, but it means at this point in time, the best we can do is estimate this. So what we'll do is we'll sketch our region. And so it's a circle. We've got our radius of a half. So I'll just indicate that along the axes here. And this is the region that we're going to be wanting to integrate over. That's our domain D. And if we want to estimate, and we know we can't, in this case, we can't find an elementary antiderivative. So the best case scenario we have is to use property f above. Then what we need to do is we need to trap our function between two constants. So that's the first thing we're going to do, is we're going to say, well, our function that we're trying to integrate over, it's going to be trapped between, well, what's the smallest that x squared plus y squared can be? Well, both x and y could be 0. And so the smallest this function could be is e to the 0. And that's just because x squared plus y squared are positive. So the sum of two positive numbers is positive. So the smallest that positive number could be is 0. What's the biggest it could be? Well, the biggest it could be is x squared plus y squared. That could be out on the boundary of our disk, so on the circle. And so this could be at most, x squared plus y squared could be at most a quarter because it's radius a half. And so that's what our function's trapped between. And so by part f above, we have that the integral over this domain, I'll just write dA here for our area element. So that integral, which we're trying to estimate, that's trapped between, and I'll do one more thing here, e to the 0, that's just 1. So this is trapped between the integral of 1 dA and the integral of e to the 1/4 dA. So that's by part f. We know that it's trapped between these two values. The next part is to just realize that that integral is just saying we're integrating over the domain D of the constant function 1. And so that's just the area of the region. That's just the area of D. And D is a disk of radius a half. So its area is pi r squared. Sorry, pi times a half squared. Or in other words, pi by 4. And similarly, this one is equal to, we can factor out the e to the 1/4, and we get the integral of 1 over the domain times e to the 1/4, and that integral is again pi by 4. So this becomes an e to the 1/4 pi by 4. And so that means that our integral is trapped between e to the 1/4 pi by 4 and pi by 4. And if we want to know, roughly what are these as decimal values, this one is 0.785 approximately, and this one is 1.0085. So that's how we can use things like that property f to get estimates for our integrals. We just bound our function. If our function is too complicated to integrate to find an antiderivative of and therefore get the exact value, we can do some estimates. How big is our function? How small is our function? And trap it between, trap the volume of that object between the volume of two simpler objects that we can compute. Now, I will make a comment here. If we want to find the exact value, the exact value of the integral, we need a coordinate system that simplifies the integral. Because right now it's too difficult. The function doesn't have an elementary antiderivative. And so since our region that we're integrating over is a circle or a disk, and we've got an x squared plus y squared in the exponent, that this seems that rather than using rectangular coordinates, some polar coordinates would probably be best. So we would use polar coordinates. And that's what our next section's about. How do we use polar coordinates to work out integrals? Absolutely, James. Yeah, you can also do Riemann sums to do an estimate of the value as well. You could do a Riemann sum and chop up your circular region into a bunch of rectangles and then do the estimates on each of those rectangles by picking sample points. So yeah, that's another way to do it. And that using those Riemann sums in that way will give you a way to control how close your approximation is to the actual value. The more rectangles you take, the better your approximation you'll get. All right, let's head off to now polar coordinate system. So now we're into section 15.3. I'm going to do a quick review of polar integrals from Math 152 by doing an example, and then we'll get into double integrals using polar coordinates, and then we'll actually see how the example that we're going to do to start off with from Calculus 2 can actually be thought of as just a particular case of this more general approach that we're taking in Calculus 3. So what was our Calculus 2 results? Well, what we had was given a curve in the plane using polar coordinates as our coordinate system. So we've got r is equal to 1 plus cos theta here. This curve is the cardioid, and it looks something like this. So there's our cardioid. And what we're interested in is finding the area of that region, area of the region bounded by the cardioid. We can make a note of a few things. This is theta equals 0. This was theta equals pi by 2. In our polar coordinate system, this is theta equals pi. This is theta equals 3 pi by 2. And what we're then interested in is finding the area of the region. And to do that, we integrate over the angles that sweep out the region. So that was going to be 0 all the way around to 2 pi. You could exploit symmetry here. You could just go to pi and then multiply the result by 2 because the upper and the lower halves are the same and have the same area. They're symmetric. But we'll go around all the way to 2 pi. And what are we integrating? Well, what we're integrating is 1/2 r squared and then our variable of integration d theta. So that 1/2 r squared was this special thing we just had to remember to use when we use polar coordinates and integration of regions bounded by polar curves. This had to do with the fact that it was related to the area of what we call a polar rectangle. I'll talk a little bit more about a polar rectangle before, but the idea was it's related to, the area of a slice of pizza. So we got an angle sweeping out and then a radius that's changing. So we had to utilize that in our Riemann sum formula, and it just comes out to that you have to involve 1/2 r squared d theta. And then once we have that, we go ahead and we pop our curve in. So this is 1 plus cos theta all squared d theta, which is the integral from 0 to 2 pi. I'll bring the 1/2 out front, and we get a 1 plus 2 cos theta plus cos squared theta d theta. And then we have to realize that cos squared theta, that's a tough thing to find the antiderivative of. So we're going to use a trig identity to rewrite it. So we'll use the double angle formula. And so that's 1 plus 2 cos theta. That's all fine. And it's the cos squared theta that we will replace by a 1/2 plus a 1/2 cos 2 theta.
So Professor, here
Yep.
the A is the area of the cardioid, right?
Correct. Yeah, the area of the cardioid.
Okay, so that's the formula right there, 1/2 r squared.
You got it.
Okay, thanks.
You're welcome. Yeah, the 1/2 r squared is the area for any polar curve. So if we've got any polar region that we're trying to find the area of, something like this here. Actually, I'll remove this part of it because we can just take the difference of two curves. So suppose I have a region like this, and this is given by r equals f theta, and this was theta equals alpha, and this was theta equals beta. Then the area of that region is given by the integral from alpha to beta of 1/2 f of theta all squared d theta. So it's 1/2 the radius squared times the angle differential d theta. So that's just our result from polar coordinates. Now, one thing we will figure out today is that maybe in calculus 2, when you first saw this, you're like 1/2 r squared. That's just a formula we're going to have to remember. You can derive it each time. I mean, it's just related to the fact that it's an area of a sector of a circle. And so if you think about it, what is the what is the area of a circle? It's pi r squared. But a circle is swept out by the angle 0 all the way around to 2 pi. So the area of a circle you can think of as it's 2 pi times the radius, and then times radius squared. So 2 pi r squared, and then you divide by 2 to get the pi r squared formula. And that's really where that half's coming from. It's basically the angle. The angle there is d theta, so it's 1/2 d theta times the radius squared. So this is just related to the area of the sector of a circle. That's all it's coming from. But I'm not going to, I won't rederive that here. That was a calculus 2 thing. We'll see how we can get it in another way using calculus 3 results, a different approach that gives you the same result. Okay, so then we're now at the stage where we've got an integral that we can compute. So I used a double angle formula, to reduce the square to get that. And then at this point now it's a couple of integrals that are straightforward, integrals of cosine and cos 2 theta. And so what we get is a result of 3/2 pi. So there's our result. That's the area of that cardioid. Okay, so that's just a brief refresher of the kinds of things we did in calculus 2 with polar coordinates. We could find areas of regions defined by polar curves. Now, what about calculus 3? Well, in calculus 3, we're going to do the same thing that we did in section 15.1. So let's just back it up. 15.1. Here we are. In 15.1, what we did was we had a region that we were interested in. And so we chopped the domain up into a bunch of rectangles. We sampled the function value on those rectangles, and we took the area of the rectangular base and multiplied it by the height of our sample point to get the volume of that rectangular cylinder. And then we added up all of those rectangular cylinder volumes to get the value of our integral, essentially, as we let the limit of these cylinders, as we let, maybe I should say it, as we let the number of these cylinders go to infinity. We're going to do the same thing here, except that in a polar coordinate system, rectangles aren't the natural thing to use. In a polar coordinate system, the natural thing to use are what we call polar rectangles. So what's a polar rectangle? It's the thing that we get where we let one of the variables range between two constants, so r between a and b, and the other variable range between two constants. So it looks like this. Theta equals alpha all the way up to theta equals beta. R equals, so that would be an R equals A all the way up to an R equals B. And that gives us this region here. And that's a polar rectangle. That's the analogy of a rectangle in the polar coordinate system. And so we need to know what the area of this is, because we're going to sample our function at a sample point inside this. We're going to take the area of this polar rectangle, multiply by the height, and that gives us the volume of this polar rectangle box. And then we're going to sum up over all of those and get our integral. So we need to know what is the area of this polar rectangle. So what is our area? Well, our area is, we can think of it as the area of, all of this stuff, this full pizza-shaped region, minus the smaller pizza-shaped region, the purple stuff. And then we get a formula which gives us sort of the area of the crust. So what's the area? And I'll say, of crust, just to give us an idea. Crust of our pizza, what's the area of that thing? Well, it's going to be the area of the blue stuff. And what's the area of the blue stuff? Well, that's the area of a sector of a circle. And so that's going to be 1/2 times the radius squared times the angle, which is beta minus alpha. So that's the area of that full slice of pizza minus the area of the stuff, the purple region, the stuff with the toppings. So that's 1/2 a squared beta minus alpha. Or in other words, we can condense this down and get that it is given by this 1/2 b squared minus a squared times beta minus alpha. So that's the area of the sector of a circle. I'm going to just rearrange this a little bit and write it in a more useful form. So this is 1/2 b plus a times b minus a. So I'm going to factor that difference of squares, and that's a beta minus alpha. And now I'm going to think, when alpha is approximately beta and b is approximately a, i.e. the rectangle, well, I should keep calling it a polar rectangle. Polar rectangle is tiny. When the polar rectangle is tiny, in other words, the angles are really close, alpha is really close to beta, and the radius r is really r equals a is really close to the radius b. So it's this tiny little polar rectangle. What we have is that the area of a tiny rectangle, which we call the area element, this is the area of a tiny little polar rectangle, that is given by what? Well, I look at my formula above. It's 1/2, and then, well, actually, let's, yeah, maybe we'll continue on. It's 1/2 b plus a. oh, but b plus a, that's approximately the same thing. So I'll say when they are approximately equal to each other, which we'll call just r, then this would be 1/2 of r plus r, or in other words, 2r. So I can get rid of the half now and just write it as r. B minus a. So that is just the small change in the radius. So that's our dr. And beta minus alpha, that's just our small change in our angle. So that's d theta. So our area element, the area of a tiny little polar rectangle, is approximately, it's in terms of these differentials, it's equal to r, the radius, times dr times d theta. So that's our tiny little rectangle, polar rectangle. So I'll draw it out here. We've got really thin angles. So this is our change in our angle. And then we've got our change in our radius. And that's our area. That's our area element that we're just working out now, how much area is there. That's our dA. And it does depend on r, right? The closer I slide this to the origin, the smaller the area is going to be. The further I slide this whole thing away from the origin, and if I slide it out here, even though the dr is the same, this area is going to be bigger. And if I go really close to the origin, even though our dr is the same, so this is again a dr, then the area is tiny. So the area of that element depends on how far it is away from the origin. That's what this r here is for. It's telling us that it does depend on how far away this little tiny polar rectangle is from the origin. And then it also depends on how thick it is and how wide it is. And that's the dr and the d theta. So that's our area of a tiny polar rectangle, or what we call the area element. And that's what we need in order to work out the integrals that, that represent the things we want them to in polar coordinates. So we start with our original integral. It's the double integral over the region of our function times dA. In this case, since we're in polar coordinates, we use the area element for polar coordinates. We're not going to use the area element for rectangular coordinates. dA would have been dx times dy in rectangular coordinates, but now we're going to use dA is equal to r dr d theta. And so that's this part here. We use our polar coordinate area element. And so now we're all set to actually start to compute double integrals in the polar coordinate system. We just have to realize that when we switch into polar coordinates, we have to add this r dr d theta instead of just a dx dy. There's a couple of corrections. The theta is, I put in red because in the notes I actually had an r written there. So this is a correction. So here's a couple of corrections. Theta, that r needs to be a theta, and there I forgot the closing parenthesis, that curly bracket on the right. Okay, so here is the big takeaway. When I'm staring at an integral of this form, and it's best done using polar coordinates, then I update my limits of integration, and I update my area element, which is the r dr d theta. So let's have a look at a bunch of examples now. Find the volume of a solid that lies below the surface and above the plane, above the planar region bounded by the curve r equals 2 cos theta. So let's get a view of what this region looks like. So r equals 2 cos theta. That's a circle that's been shifted over. So if we think of this as being like our xy, just to translate between that and the polar coordinate system, then this is r equals 2 cos theta. It's shifted over to 1, and it goes all the way out to a value of 2. So it's a circle of radius 1. I'm going to try to draw a better circle here. Something that actually looks like a circle. So circle of radius 1. Okay, so that's just borrowing from the Calculus 1, Math 150 or 151, sketching polar curves. So that was something we did there. So we can sketch this curve. Now that we've got that curve sketched, what we're interested in doing is integrating this function, x squared plus y squared, over that domain. So we're interested in finding the volume, which is the integral over the domain of x squared plus y squared dA. That's the integral we want to evaluate. And what we could do is we could notice that there is some symmetry here. We could exploit the symmetry and just note that if I integrate instead from theta equals 0 around to theta equals pi, that sweeps out half the circle. Now the point is that just that alone, symmetry of the domain, is not enough. I also need the function to be symmetric on this domain, and the function is x squared plus y squared. So that is symmetric about the x-axis as well. And so what we can do is we can use symmetry here. So I'll go multiply by 2. So I'm using symmetry. And my angle can go from 0 to pi by 2 then. 0 to pi. Oh, actually, we got to be careful. I actually have to be really careful here in the following way. So I wrote down theta equals pi, but here's the thing. When I'm actually traveling along the curve, this is theta equals 0. So I plug in theta equals 0. That's cos of 0, which is 1. And that gives us our value of 2. And then as I start to go around the curve, then what I end up with is when I hit this point, that actually corresponds to theta equals pi by 2. Because let's think about it. As we plug theta equals pi by 2 in to our curve, cosine of pi by 2 is 0. So the r value is 0. That means this point down here corresponds to theta equals pi by 2. And then as I keep going, I come all the way around to here. And this also corresponds to theta equals pi, that point. And that's because the r value is negative and it would have shot across the pole. So we have to be very careful when we think about the angles in this case as to what points are being traced out. So to get the upper half of the circle, we just go out to pi by 2. And then the r values. Our r values are going to, we want them to sweep out the entire region. So our r values are going to look like this. We're going to be sweeping out our region in this way. So our r values are going to go from 0 all the way out to the curve, so 2 cos theta. And then we've got our x squared plus y squared. So that's going to be, in this case, let's just think about that for a second. So polar coordinates, x squared plus y squared, that's the same as r squared. So our function we're integrating becomes r squared. And then we've got an r dr d theta. That's our area differential, or our area element. And this was our function that came down here. And so now we're set up to do our integral calculation. So that's 0 to pi by 2, the integral from 0 to 2 cos theta, r cubed dr d theta. And this is where one of those results that we talked about earlier in section 15.1 comes in handy, because I noticed that this integral doesn't actually have, actually I can't do this. I was going to say the integral doesn't have a theta, but It does. The theta is hiding in the upper limit of integration. So I would have loved to have split this integral into two, but now on second glance, I'm like, oh, there's a theta hiding in that. So I have to do the integrals inside to outside. I can't split them up into two different integrals, a product of two integrals. So then we can go ahead and go 2 times the integral from 0 to pi by 2, a quarter r to the fourth. That's going to be evaluated from 0 to 2 cos theta. That's d theta. And then that becomes a 2 times the integral from 0 to pi by 2 of a quarter. I can bring the quarter out front as a half. And then I get a cos 4 theta d theta. And so now that's the that's the integral that I'm going to be interested in. Let me see, I might have, oh yeah, I was going to say I seem to be missing a factor. There was a 2 in front, so it's actually a 2 to the fourth cosine to the fourth of theta. I forgot about that 2 that's sitting in front of the cosine in that upper limit of integration. And so this becomes then an 8 times the integral from 0 to pi by 2 cos 4 theta d theta. Now at this point, we need to integrate cos 4 theta. We can do this by hand. This is certainly within our realm of possibilities to do by hand. However, this is not one that I would ask you to do on an assessment because it's a little bit more cumbersome. So if you're working on a homework assignment and you're at this point, you can certainly practice your integration skills by doing this by hand, or you can just throw it into Wolfram Alpha and have it compute it. How would we do it by hand? Well, the first thing we would do is we'd say, well, cos squared is 1/2 plus cos, 1/2 plus a half cos 2 theta. Just back it up, plus a half cos 2 theta. So that's a double angle identity we could use. And then I could square both sides of that. And if I square both sides of that, then what I get is a formula for cos 4 theta, which is a quarter plus a half cos 2 theta plus a quarter cos squared theta, cos squared 2 theta. And then I'd again use that formula down here to reduce that cos squared to just a cos. In this case, it would be a cos of a 4 theta. So there is using identities to reduce this. So there's a possibility. However we do it, we will get a result in the end of 3 pi by 2. Okay, so the emphasis here wasn't on the integration, it was on the setup, doing the polar coordinates. Okay, let's have a look at, yep, go for it.
I had a question regarding the graph. How do you know it was centered at 1?
So this short answer is, I remembered from Calculus 1. Long answer is the following way. We want to, so the idea is, the long answer is, if we were introduced to polar coordinate systems in elementary school, where we're introduced, like I think it's grade 7, you're introduced to rectangular coordinate systems. But instead, if we lived in a world where polar coordinate systems were the go-to coordinate system, then this would be a curve that you would look at and you go, that's a circle. I know that. Much the same way you look at a x squared plus y squared equals 1, and you're like, that's a circle. So this in polar coordinates is a circle that's shifted over. How we get that, that's the nature of your question, which is a good question. So how do we get that? Well, the way I could get that is as follows. R equals 2 cos theta. And because I'm used to thinking in rectangular coordinates, then I'll try to convert this to rectangular coordinates. So to do that, I would go, well, r cos theta, I know is an x. So I'll introduce an r up top and an r down below so that I could write that as 2x over r. So I artificially insert this r up top and this r down below so that I can get an x appearing in there. And now I have r squared is equal to 2x. And so then I get an x squared plus y squared is equal to 2x, because now I can replace the x squared plus y squared with, sorry, the r squared with x squared plus y squared. And that means now I can bring the 2x over and get an equation like this, which now I can recognize as the equation of a circle. I just have to complete the square to finish it off. So that becomes an x minus 1 squared plus y squared is equal to 1. And that's our circle that we have there. So that would have been a calculation that we did in calculus 1. But yeah, thanks for the question. And that's a good reminder for us now.
Yeah, no worries. So in the test or in a question, so basically we should do that to know how to graph it, right?
Conceivably, this is true. However, in a test, because this is calculus 1 material, and I'm more interested in testing you on the calculus 3 material, it is most likely, if I'm going to give you a curve that's sort of a non-standard one, I'll give you the graph as well. Okay. Yeah, I don't want to put the emphasis on testing calculus 1 material when it's really about the integration that's more interesting to us here.
Yeah.
Yeah. So thanks for that.
Yeah, no worries. Thank you.
So let's consider now this double integral. What we have to do in this case is read off from the integral what the region is we're integrating over and see if it's better done in another coordinate system. So this first part, sketch and describe the region of integration. Let's see what it is. Well, reading off from the picture, we have that x is our first variable of integration. So it's trapped between, it goes from y up to pi minus y squared. And what does y go from? Y goes from 0 to root pi by 2. Okay, so that's just reading from the integral the limits of integration for the respective variables. And so now I can go ahead and try to sketch this. I've got that there's an x equals y boundary. So that's, I know that x has got to be bigger than or equal to y. So the boundary would be x is equal to y. So that's a line that looks like this. So that's our x equals y line. And then I have that x is at most square root of pi minus y squared, or in other words, x squared plus y squared is less than or equal to pi. So that's a circle. So I know that I've got a circle that I'm dealing with as well, about the origin of radius pi. And I know x has to be trapped between these two. So x has got to go from the line out to the circle. So I'm in this region here. And that corresponds with the y values as well, because y is going to trace out all the values from 0 all the way up to this intersection point, and that is a root pi by 2, because that's essentially a 45-degree angle, and so I can read off the y value from that particular point. So this is my region. I'm looking at the sector of a circle. And so now we can convert to polar coordinates. So what we're going to do is we're going to say, okay, for polar coordinates, what is our integral? Well, our integral, our angles go from 0 up to, in this case, this is pi by 4, because that's the line x equals y, so that's at 45 degrees, or pi by 4. So we're going to go from 0 to pi by 4. What are our r values doing? Well, our r values are starting at 0, and they're going all the way out to the radius of this circle here. This is an x squared plus y squared is equal to pi, so its radius is equal to root pi. So our r values go from 0 out to root pi. And now we look at this and we say, oh, all the limits of integration are constant. And that's because this is a polar rectangle. So what was a region that was tough to describe in rectangular coordinates, it's actually just a polar rectangle. So it's going to have constant limits of integration in the polar coordinate system. And then we continue on. What's our function? Sine of x squared plus y squared is equal to r squared. So that's sine of r squared. Right. So for this, replacing our function, we just take the x and replace it with r cos theta, and we take the y and replace it with r sine theta. And in this case, x squared plus y squared then becomes r squared. So that's the first observation. The dx dy, that becomes an r dr d theta. And so this becomes the integral from 0 to pi by 4, the integral from 0 to root pi of r sine r squared dr d theta. And that's really nice because now we can use substitution. The derivative of the r squared is sitting right out front. It's the r. Here's where another thing I'm just going to draw your attention to. I noticed that there's no variable theta appearing anywhere other than in the differential d theta at the very end, the variable of integration. So that means we can use one of these properties that says we can just split it up into two integrals. The integral involving the theta and the integral involving the r.
Professor?
Yep.
Could you explain one more time how you got the limits, the 0 to pi over 4 and 0 to root pi?
Yeah, I'm looking at this particular region here. And so I imagine what happens when my theta values sweep out that region. So my theta values go from 0, they keep increasing in angle until we get to pi by 4. So that's my theta value sweeping out 0 to pi by 4. My r value, I imagine I'm standing at r equals 0. And what do I have to do to get out on these? So I'm along any one of these lines. So maybe I'll go back and I'll draw one of these arbitrary theta lines. Now, what does my r value have to do? My r value starts at 0, and it's got to sweep out that entire line to get out to here. So my r value goes from 0 all the way out to the point on this circle. And this circle has radius pi. Sorry, the circle has radius root pi because the equation is here. And so the radius is the square root of the right-hand side of that equation.
Wait, but why is x squared plus y squared equals pi?
Because that's coming from that part of the limits of integration. X had to be trapped below by the square root function, which we just rearranged and recognized as a circle.
Mm-hmm.
So then this... Oh yeah, go for it.
Okay, I get it now. So basically you just took the square root of x squared plus y over squared because that's r squared, and then you got root pi. Right?
Yeah, you got it. Yeah.
Yeah, okay, thank you.
You're welcome. And so this integral, that becomes a pi by 4. And so that's nice because now we've dealt with the theta stuff. The other integral is what has a derivative of r sine r squared. That would be a negative cosine r squared. And you'd have a half there like that. So I'm just doing the antiderivative in my head. It's an antiderivative of the sine, which is the negative cosine, and then adjusting for the fact that there was a chain rule that would have been applied when you took the derivative. So we have to account for that. And then that's from 0 to root pi. And so this becomes a pi by 4. And that's a negative 1/2 cos pi plus a 1/2 cos 0. Cos pi is negative 1. Cos 0 is 1. So this becomes a half plus a half, or in other words, a 1. And so the result is pi by 4. Okay, so that's this step here, this step I'm indicating by a star. That's always just something to keep in mind. If you scan through your integral and you're just like, oh, I don't see a variable, the d theta or the theta is not appearing anywhere. Oh, that means I can just strip off that integral and do it on its own. So that was one of the results we had at the very end of section 15.1. Okay, let's have a look at this next one. This is, I believe I put this on the homework, so I'll leave it for there. It's just a nice example where it says we can actually use multivariable techniques to answer questions about single variable integrals. And so I'll leave it.
Go up for a second.
Yep. And then
1 second.
And so then the next thing I want to do in the, we got about a minute left. So I'm going to do example 7, and then I will.
Thank you.
Oh, you're welcome. Then we'll do example 8 at the beginning of class next day. So example 7, you may look at this and go, oh, that's deja vu. This is exactly the question we had right at the start, motivating this material on polar coordinates and saying, you know, we've done it in calculus 2. Now let's see how it translates to calculus 3. There was that 1/2 r squared that comes up in that formula. So I'll scroll back to it. From calculus 1, we get this 1/2 r squared that appears here. And that's related to the area of a sector of a circle and the like, and you get that in the Riemann sum. So we did a whole in calculus 2, you do a whole section on trying to motivate why this is the formula we get and then doing examples on it. But now I'm going to come back to that and say, we actually get all that for free now, because every time we learn something new in this course, it has the potential impact of making previous stuff we've learned in earlier courses as specific examples. And so here, what are we interested in? We're interested in finding the area of the cardioid. We want to find this area here. So what we could do is we could say, well, the area of the cardioid is precisely the integral over that domain. So I'll call that domain D of the area increment, or the area element, so dA. So what is area? Area is the area of the region D is the double integral of 1 dA. You want to think of it this way? We are integrating we're finding a volume where the height is 1 over all of these things. And so since we're finding the volume where the height is 1, a constant height, then really what we get is the volume is the area of the base times the height, or the area of the base times 1. So we get that the volume is precisely the area of the base. So in other words, this formula just gives us the area of the base. And what is this? Well, this would be the integral from, we would go theta goes from 0 all the way around to 2 pi. R goes from 0 up to the curve 1 plus cos theta. So again, I'm imagining these rays sort of sweeping out the region. Those are all of the theta values that sweep out the region. For any one of those theta values, our R value goes along it out to the curve. So that's how I sort of get these limits of integration. dA in this case is R dr d theta. And now we can go ahead and integrate. When we integrate, we get the integral from 0 to 2 pi. We get a 1/2 r squared, 0 to 1 plus cos theta d theta. That's where the 1/2 r squared comes from in our calculus 1 formula. It comes from the integral of r. And so this becomes the integral from 0 to 2 pi of 1/2 1 plus cos theta squared d theta. And we can get the result. Now we have the integral from before. So the idea is you can avoid having to memorize the formula from calculus 2 about the integral of 1/2 r squared d theta, because it just follows from this formula and our area increment, or area element, r dr d theta, replacing dA, for calculus 3. So this, every time you learn something sort of new in higher level math, it has the potential of going back and just saying, oh, you don't need to remember that specific formula because it's just a particular case of a more general result. And here's the more general result we have. All right, so that's it for today. I'm going to stop the recording.